Thanks. Okay, thanks very much. It's great to be here. I'm really excited about this conference in general. So today I'll be talking about Bayesian machine learning for quantifying uncertainty and robustness in scalable data analysis problems. And in particular, I'm going to illustrate the benefits and the challenges of Bayesian machine learning by focusing on a couple of examples. So these examples include microcredit. So these are these small loans to individuals in impoverished areas. And the hope is that we'll help raise people out of poverty. And we want to ask, are they actually effective? Also look at online advertising as an example where we really have extremely large-scale data and problems. Now, the things that I'll be talking about today are going to be illustrated with these examples, but fundamentally I'll be talking about developing a toolbox for data analysis. And so in particular, I want to point you first of all to the work of Rachel Meager. So she's our collaborator, she's fantastic, she's an economist. If you're interested in the economic analysis of microcredit, I really want to emphasize that you should go check out her paper. It's really great. I'll be talking about how we can again develop a toolbox for people like Rachel for practitioners. So in particular, in the case of microcredit, we have data, Rachel has data, on sites in 7 different countries, ranging from Mexico to Ethiopia. And at each of these sites, a randomized controlled trial took place. So each one of the businesses, there were between about 900 and 17,000 businesses per site, either received microcredit or it did not. And again, we want to ask, is microcredit actually helping people? Is it doing something here? It's a very broad, vague set of questions, and so we might narrow down a little bit more to something specific, like how much does microcredit increase business profit? Now this is an unknown, it's a parameter of the model, we might call it tau. And then we might say that, a priori, we don't know anything about tau. Tau could be positive, we certainly hope it's positive. But it could be that microcredit is actually not doing anything or it's hurting people. At least we don't know until we've looked at the data. So tau could be 0, it could be negative, we don't know just yet. So we'd like to do a data analysis to figure out, is microcredit helping? And we have various goals as part of this data analysis. So for instance, we really want interpretability. In this particular case, what I mean by interpretability is that we have certain quantities that we're interested in this data analysis, like this microcredit effect. How much is microcredit increasing business profit? But other things like how much is it increasing business profit in each country? What's the base business profit in each country? What's the base business profit overall? And many other things that we're interested in. And we want to pinpoint exactly those quantities of interest. So that's something that's interesting to us here. Another thing is we want to quantify uncertainty. So this is very important for the decisions that we're going to make at the end of the day. Let's say I find out that tau is on average $2 purchasing power parity every 2 weeks. That's how much microcredit is increasing business profit. Well, is it $2 plus or minus 0.1 cent? In which case, yeah, microcredit. It is definitely helping people. We should invest in it. Go microcredit. Or is it $2 plus or minus $10? In which case, maybe microcredit is ruining lives, and we don't know. And we definitely shouldn't make jump into investment decisions until we get a better analysis going. So in order to make these decisions, we really care about uncertainty. And the reason that I say coherently is that I find that there's a lot of feedback on this. So I'm going to just put it down here. So we find that, in fact, there's a lot of, again, quantities that we're interested in here, not just the microcredit effect, this global microcredit effect. And so we want to get uncertainties that are coherent, that don't come into any sort of conflict across the various parameters of the model. We also want to share information across experiments. So this is a little bit of a subtle point. We might imagine that maybe we're just going to combine all of our data from Mexico to Ethiopia into one big stack and say, we're going to treat this all like it's from the same country. But, again, a priori going into this, we don't know that the businesses in Mexico are affected by microcredit in the same way that businesses in Ethiopia are. And so at least, again, a priori, we might want to separate those out or at least respect that they're idiosyncratic. On the other hand, we don't want to just analyze all of the data from Mexico and then throw that away, and then analyze all of the data from the Philippines and then throw that away, and so on, because one, we're not able to share the power that we're getting from each of the data sets across the data, but two, we're not able to predict at a new site that we haven't seen before, which is certainly something that would be of interest in this application. And so we want to, again, be able to share power, but in a way that lets us actually combine this information in a non-trivial way that lets us respect the idiosyncraticness of each country. Okay, so all of these desiderata, all of these goals are achieved by Bayesian machine learning, by Bayesian methods. In particular, the use of parameters lets us pinpoint exactly what we're interested in terms of interpretability. The ability to quantify uncertainty comes out naturally because the output of Bayesian methods is a probability distribution over our unknowns, and probability is the language of uncertainty. Finally, we can share information across experiments by using hierarchical modeling and graphical models. In fact, more generally, this lets us capture complex physical processes, complex biological processes, all kinds of things that might come up as well. Okay, so these are reasons to use Bayesian methods. They certainly seem relevant in this particular use case. So what remains to be done? Well, let me highlight a few challenges. So one is we want to get fast results. Traditionally, these methods can be somewhat slow. We want to deal with thousands of data points, millions of data points, billions of data points. Let me make a couple of sort of subtle remarks about this, though. When I say fast results, I don't just mean that we have a billion data points. Sometimes, if you have a particularly simple problem, a billion data points doesn't need to be that bad. You could have a complex problem, and a few data points could be challenging. You could also imagine a situation where maybe you're not a company, and for the computing you have, maybe you're a researcher, you just don't want to wait around all day for your results. You want to be able to get something fast so that you can prototype and move on. Also, another fallacy that often comes up when people are thinking about large-scale data is that if I have enough data, all of my uncertainty goes away, and I want to challenge that in fact that's not the case often. So for instance, imagine that you're Amazon or eBay. Sure, you have a ton of data, but you also have a ton of products. And if you think about the long tail of products, there's actually a lot of uncertainty, maybe not even a lot of data for a lot of those products. Or if you think about people driving and we're maybe trying to decide where an ambulance goes or where an individual should be routed, there may be not a lot of people driving a particular road at a particular time, and we don't have a lot of data about that scenario. Okay, another challenge is that we want theoretical guarantees. I can come up with some extremely fast, extremely bad algorithms. And so I want something that, of course, is fast and right. And this is something that is easy to lose track of, but we really want something that is verifiably going to give us the right answer. And in the real life cases that we have, sure, we have a lot of data, but our data is still finite of necessity. Maybe we have a lot of running time and a lot of resources, but it's still finite of necessity, and we want to know for what we have, what we can do. Now, these points that I'm talking about aren't specific to Bayesian inference. These are things we're generally concerned with, and this is also true of the final point. We want robustness quantification. No matter what you're doing in data analysis or machine learning, I can guarantee you that there are assumptions built in to that. And we would like to know how robust our outputs are to those assumptions. If we changed our assumptions a little bit, would our outputs change a lot? In which case, we might be concerned that our assumptions are not robust, and maybe those decisions we're making are not the right decisions. Okay, so we want to deal with these things, and in this talk I'll talk about how we can start to achieve this fast results, this robustness quantification with theoretical guarantees. And I'm going to start by thinking again about this microcredit problem. Okay, so in particular, let's think we want to do this thing, we want to quantify uncertainty. How can we do that? Well, remember the output of a Bayesian inference algorithm, a Bayesian inference procedure, is a distribution, a probability distribution. So here I'm showing a two-dimensional distribution, the contours of a two-dimensional distribution over, let's say, tau. That could be how much is microcredit increasing profit, and mu, the base business profit. Now in reality, in this problem, and basically any other problem, the number of parameters is extremely high. And so this will be an extremely high-dimensional problem, but we as humans can sort of only see in 2 dimensions, and so I've shown you this cartoon of a 2-dimensional distribution. Now the distribution that's returned by a Bayesian procedure is known as the posterior distribution because it's posterior to having seen the data. And we wish we had access to the exact posterior provided by theory, but we don't in practice pretty much for any problem, so we have to approximate it somehow. Traditionally, this has been done with Markov chain Monte Carlo. It's been named one of the 10 most influential algorithms of the 20th century. It's accurate if you run it long enough, and you often don't have long enough. So what do we do instead? Well, increasingly people have been turning to so-called mean field variational Bayes because it's very fast. Problematically, it can underestimate uncertainties, in fact, arbitrarily badly. So for instance, even if I just take this tiny cartoon, this 2-dimensional simple cartoon, and I fit mean field variational Bayes to it, this is the approximation I get. You don't have to know anything about probability to see that the red thing does not fit the green thing very well. And in fact, it's a particularly dangerous direction that it's going. So remember, uncertainty is kind of like the width here. It's underestimating the width. You're being overconfident in a way that is not supported by the data. Okay, and there are no estimates of correlation as well from this. Okay, so we provide, as a correction to this, linear response variational Bayes. You can see this, we get this idea from perturbation ideas from statistical physics, and you can see it as a correction to mean field variational Bayes. So the idea here is that you run your mean field variational Bayes algorithm, you get out your bad block diagonal underestimating covariance matrix, let's call it V, and then you correct it. You correct it with a matrix that's composed of I, the identity matrix, V, that's the same V that I just mentioned, and H, a matrix that comes from the form of the problem and automatic differentiation. Finally, we get our correction, let's call it sigma hat, our LRVB estimate of the uncertainty. If we were in fact dealing with a multivariate Gaussian posterior, this would exactly recover the covariance matrix. More generally, this will be an approximation. So again, I just want to emphasize the setup here is we first run mean field variational Bayes, we hope that's very fast, and then we correct it with linear response variational Bayes. Okay, so how well does this do in practice? Let's look at an example. Let's look at this microcredit experiment. For a particularly simple model here, we could compare it to Markov-Chain Monte Carlo, because again, we don't have ground truth, we don't have the exact posterior, but we could run Markov-Chain Monte Carlo for a long time to see how we're doing. In this case, we can use a popular Markov-Chain Monte Carlo package. It takes on the order of 45 minutes, whereas all of mean field variational Bayes, followed by these linear response corrections, followed by a bunch of sensitivity measures I haven't told you about yet, but I will, takes about 58 seconds. And so this kind of order of magnitude speed up can be a really big change for somebody like Rachel Meager or somebody who's a practitioner who's going to iterate on a lot of models. Okay, what are we seeing here? So we're comparing our LRVB estimates of the posterior means to the MCMC estimates. And we're also comparing the MFVB estimates. So each point is a parameter in the model. Red is LRVB, blue is MFVB, and x equals y is the black line. And so you can see that mean field variational Bayes is systematically underestimating the uncertainties, the standard deviations in this case, whereas mean field variational Bayes is getting them right. How does this influence your life? So imagine that you've come in and you've said, okay, I'm going to decide whether microcredit is effective. And I run my analysis and I found that the mean microcredit effect, the mean amount that it's increasing business profit, is $3 purchasing power parity every 2 weeks. And I found that the uncertainty in that, the standard deviation, is $1.83 purchasing power parity, and so the mean is 1.68 posterior standard deviations from zero. Now you might have said going in, hey, if the mean were more than 2 standard deviations from zero, I would say this is a substantive effect, I'm going to go out and invest in microcredit, I'm going to make some big decisions, I'm going to go gung-ho for this idea. But if it's fewer than 2 standard deviations, I don't feel like I have enough data yet. Maybe I'll go back to the drawing board, think about maybe getting more data or experiencing, whether there are covariates that really matter here, maybe whether or not somebody's had a business before, things like that, that could be influencing this. And the key point here is that if, in fact, we had used mean field variational Bayes to estimate the uncertainty, we would have erroneously underestimated it, to the point where we would have thought the mean was more than 2 standard deviations from zero without support from the data, and we would have jumped into an investment decision that was not supported by the data. And so we really need these uncertainties, these correct uncertainties, in order to make these decisions. This is not, again, specific to microcredit. Imagine an ambulance routing problem. Maybe I have route A over here and route B over here, and route A takes on average 9 minutes to get to the hospital, and route B takes on average 10 minutes, and you might be thinking to yourself, ooh, we should always take route A. But if you need a life-saving procedure in 13 minutes, and this is 9 plus or minus 5, and this is 10 plus or minus 1, you might actually really want route B. Okay, so we want these uncertainties, we want to get them correctly. The next thing I'm going to talk about is slightly related to the idea of uncertainty, but it's a little different, this idea of robustness. Again, any data analysis algorithm that we use will have assumptions baked in, and we want to know how sensitive our output is to those assumptions. So for instance, let's think about Bayesian Inference, just as an example. We start off, the way that Bayesian Inference works, let's just remind ourselves, we start off with a prior. Our set of beliefs are collecting our set of beliefs in a distribution before we've seen the data. Now again, this will typically be high dimensional, very complex. Here I'm just showing a one-dimensional prior because of, I have to put it on a slide. And so we take this prior, we take our likelihood that shows how the data relates to our parameter, we put them into Bayes' theorem, and we get a posterior. So in general, the prior will be more diffuse because we don't know too much before we've seen the data, and the posterior will be more concentrated because we've learned something after having seen the data. Our uncertainty should be lower at this point. Now, our assumptions in this case come into both the prior and the likelihood. But we want to be able to just pinpoint one of these for now for illustrative purposes, so I'll just pick the prior, sort of arbitrarily. And I want to point out that there could be many reasonable priors that we could choose. Maybe we find it difficult to actually put our beliefs into the form of a distribution. Maybe we all find, we're all perfectly happy putting our beliefs in the form of a distribution, but we're all very busy people, and so you only have an hour, and you do what you can, and then you got to get back to the job. Maybe I have a certain set of beliefs about microcredit, and you have a certain set of beliefs about microcredit, and they're not quite the same, but we think we're both reasonable people, and so therefore, once we have put those beliefs in, we should be able to get something out that looks the same decisions. Or maybe I have a set of beliefs about microcredit, and you ask me next week, and they're a little bit different. I want to know that I'm going to get the same decisions out anyway. And so I want to be able to say that, hey, when I apply Bayes' theorem, my posteriors are so close as to be indistinguishable, or at least my decisions are the same. And I would be very worried if instead what happened was I got two very different posteriors and two very different decisions. In this case, maybe I don't really trust that decision, and I want to go back to the drawing board with my analysis again. Okay, so for this, we want to be able to quantify robustness. We want to be able to quantify sensitivity. And in this case, I think it's even more obvious why a perturbation argument is the right type of argument. We have a set of assumptions, and we want to perturb them a little bit. We want to change them a little bit and see what happens. And so again, we can use linear response variational Bayes. In fact, it turns out our linear response variational Bayes estimate of the sensitivity first contains exactly the linear response estimate of the covariance that we already calculated, which is great. That's more computation that we don't have to redo. And then we have another matrix that we multiply by, but this is something we can get from the form of the problem. So again, we want to ask, okay, how good is this estimate of the sensitivity? Well, I want to highlight that it actually gives sensitivities in all perturbation directions if we change our prior in any different way. But in order to test how well it's doing, we're going to consider changing our prior in a particular way and just compare. So the setup here is we take a particular hyperparameter of the model, something that describes our prior. We choose those two values, we run MCMC at those two values to get a full posterior approximation from MCMC, and then we compare the difference in posterior means according to that, and that one predicted by LRBB. We have 1 point for each parameter, we have the black line as the x equals y line, and again we're seeing that we're getting good estimates. So again, how does this affect your life? You're doing a microcredit analysis. Well, imagine that you did the microcredit analysis we just talked about. We found that the posterior mean for the choice of likelihood and prior that you made was 1.68 standard deviations from 0. But there was a perfectly reasonable other choice of prior that you could have made. Under a perturbation, we find that in fact, the mean would be more than 2 standard deviations from 0 then. You might have gone out and invested in microcredit. Now in this direction, I don't think too much is going to change. You were already deciding to be a little bit more conservative up here, and maybe you're probably going to stay that way. But imagine if things had gone the other way. You started with this prior and likelihood, you were about to go gung-ho and invest in microcredit, and then you found that under reasonable other choices of the prior and likelihood, you would not have. This might encourage you to be a little bit more conservative, to think about what's different about these assumptions. Are they reasonable assumptions, or is there something going on in the analysis that you don't fully understand? Okay, so robustness quantification, uncertainty quantification, these are things that we want in our analyses, but of course something that we want in addition is to have a very fast analysis. So the types of, or the size of the data that I was thinking about in the previous example gets into sort of the tens of thousands, maybe hundreds of thousands of data points, but certainly there are many applications nowadays where we easily get into millions, billions, and trillions of data points. And so let me just name a few examples of such applications where we still care about things like uncertainty. So one of these is something like online advertising. Suppose that we have people who are clicking on our ads and we want to know, hey, for this customer, are they actually going to buy a product after clicking on the ad? And in particular, not just are they going to buy a product, but how predictive of them buying a product are certain features of the ad, like where it's placed, the text that's in it, things like this. This could be really useful if we want to do some follow-up analysis, maybe change our ads in some way, etc. Something I want to emphasize about this is that this sort of motif is very much not specific to online advertising. It comes up in all kinds of application areas. So, for instance, consider web spam detection. So there are a lot of web pages out there that are trying to get your personal information, that would like you to install something that you would not like to install on your computer. We would like to be able to not only have your browser decide, is that a web spam, is that website spam, but also what is it about that website that's predictive so it can do a better job in the future or look into that kind of information. We could also be interested in a land management application. We want to know what type of forest cover is over different parts of a forest. We might be interested in whether or not a chemical is reactive, whether or not DNA is coding, and how well we can predict that. Okay, and again, we have a variety of goals that are very similar to the previous goals that we identified in our last analysis. One, we want interpretability. We want to be able to pinpoint for each feature how much it's predicting whether or not I have, say, web spam. We want to quantify uncertainty. Maybe I find that, in fact, feature A is very predictive of whether or not I have web spam, and I'm certain of that. And feature B is very predictive, but I'm actually extremely uncertain of that. Maybe I want to devote follow-up resources to figuring out, hey, how much does feature A actually affect the spam content of web pages? And of course, I want to get fast results. I mean, especially when I think about web-scale data, these are cases where I have tons of data points. In fact, the data points can be streaming. I can't save them all in memory. There are so many of them, so I'm always getting new ones. I might have them distributed across different nodes just by the nature of their collection. I might want to distribute them in order to distribute computing time, and so I want to get these fast results. And here again, we're thinking now in terms of millions and more data points, so we need something that is truly very fast. Okay, so how are we going to deal with this? How are we still going to get these, meet these goals, but deal with this large-scale problem? And the approach that we've been taking is what we like to think of as a data summarization approach. And the sort of high-level intuition here is that you can have redundancy in your data, even if it isn't classically tall data. It's not just a bunch of copies of sort of the same thing. So just as a toy example, imagine that I have some sports corpus. Each data point represents sort of maybe a document that's about sports. And so I have a lot of baseball documents because baseball is pretty popular in the US. And maybe I have a few curling documents because the Winter Olympics just happened, and maybe one day curling will pick up in popularity, but right now it's a little bit less popular. And I want to think to myself, hey, I'd love to run maybe my machine learning algorithm on this. And unfortunately, I have a ton of data. Maybe this isn't all of it. I have, just tons and tons of these articles. Something that would make it a lot faster is if I made the observation that, in fact, any algorithm tends to be at least linear in the size of the data. And so it would be a lot faster to run on a smaller data set. So maybe what I could do is I could pick out some representative baseball article and just give it a really high weight, because there are a lot of articles about baseball in my original data set. I could pick out a representative curling article and give it a small weight, because there aren't so many articles about curling in my original data set. And now if I ran my machine learning algorithm on this data set, it would be way, way, way faster. Okay, well that's a nice idea. In fact, it's an idea that exists in the theoretical computer science and computational geometry literature, this idea of pre-processing the data to get a smaller weighted data set and then running some kind of algorithm on it. And it's called a core set, because it gets at the core of the data set. And I think what's particularly exciting about this work is not just that you could do this idea, but that you can get theoretical guarantees on the quality of inference when you run your algorithm on this smaller data set. So this is something that we'd like to have for Bayesian inference for machine learning in general. Okay, so why don't I just use a really classic idea, and in fact a really powerful idea of data subsampling? So something that actually really helps a lot in a lot of data analysis algorithms is you have your giant data set, and then you just uniformly at random subsample that data set. You uniformly at random take a bunch of data points from that data set and then just run your algorithm on that. That can actually be extremely effective. So what might go wrong here? Well, imagine that I'm working for a curling manufacturer, and we're talking about, how can they better advertise in my sports magazine, and I subsample my data uniformly at random. You can see what might go wrong. Suddenly I don't have any curling articles, and that's kind of the whole point. And so this is, a toy example, but this kind of thing comes up in a lot of other areas. So imagine that, in fact, what I care about is cybersecurity. And I'm interested in subsampling my data and then analyzing that data. Well, if there's a very small subset of malicious packets in my web traffic, I might subsample that away. Or imagine that I'm interested in a health outcome, and I subsample my data, and I care about some rare, disease that's happening in that data, or some rare, outcome. I might subsample that away. And so I don't want to do that. I want to avoid that. What can I do? So we developed these data summarization methods as a sort of more subtle way, more careful way of getting at data summarization for Bayesian inference. And in particular, we look at two methods. So one is this core sets method that I described. Another one builds on a very old and useful idea from statistics called sufficient statistics. So the idea of sufficient statistics is, again, a data summarization method. And in fact, it lets you have trivially streaming, trivially distributed algorithms. But you don't generally have sufficient statistics for your problem. So we develop a notion of approximate sufficient statistics instead. Okay, how might we get around this problem? Well, just as a high-level intuition, imagine that I knew up front that these curling articles were very important. So I could give them a much higher weight, an importance weight. Now, if I sample according to these weights instead of uniformly, I'm likely to get a curling article because they had such a high weight, and I'm likely to get a baseball article because there were so many of them. And finally, I can invert these weights and I get something that looks like my original desired core set for this data set. Now, it turns out we can get a notion of these weights from the likelihood in Bayesian inference, and in fact, we can even do better than importance sampling by using a Frank-Wolf-style optimization algorithm. Okay, let's just see really briefly how this works on real data. So in particular, Criteo is this online advertising firm. They released an extremely large data set for the machine learning community to use. So that's nice. Just to give you a sort of vague sense of what we might be expecting going in, we've done previous work on mean field variational Bayes, making it streaming, making it distributed, and we find that we can run on 3.6 million documents from Wikipedia using 32 threads in a matter of hours. In this case, we'll look at 6 million data points from this Criteo data set with 1,000 features. We can make our method, again, trivially streaming, trivially distributed, and run on a number of different cores, but in particular, notice that for 22 cores, we take about 16 seconds. So that's great. For 6 million data points, that's a pretty fast algorithm. This involves minimal communication, which helps with the speed, and it comes with theoretical guarantees on the quality of inference, which is, again, a big step up. Okay, so again, in this talk, I've gone over sort of two illustrative examples, microcredit and online advertising, but I want to emphasize that this is really a toolbox that's not specific to those examples that can be used in a lot of other applications. Applications that have these sorts of desiderata, that we want interpretability in the sense that I described, that we want to pinpoint, there are these interesting parameters that we want to learn about, that we want to get uncertainty quantification for those parameters, that we want to share information across experiments and more generally maybe deal with complex physical, biological, social, etc. phenomena. Okay, so up here I have some examples of papers if you're interested in learning more about this work. It's not all of our papers on this work, but it's a good place to get started. So there's some papers about the core sets work, some papers about the covariance, robustness, and linear response variational Bayes work, and a paper about the approximate sufficient statistics work. And then I'll just highlight, I know we had the poster session already, but I think there's still time to look at the posters. So I'll highlight that my awesome undergraduate student, Uma Roy, is working on distributing this linear response variational Bayes idea. And my fantastic graduate student, Miriam Schiffman, is working on something that I sort of only hinted at, but is a real strength of Bayesian analysis, this idea of capturing really complex processes within the data, and in particular capturing tree structure that looks at the cellular differentiation process that we can see in single-cell RNA sequencing data. Thank you.
Question.